fairly and completely everything that was discussed here. We had so much interesting science, so much interesting data. It's virtually impossible. But I made a serious effort here. I was not reading any emails or typing on the computer. Instead, I was writing many, many notes about every single talk that every one of you gave, and I put them on here. And this is a mess because this is a stream of consciousness. These are all of the notes that I took just as I'm typing them when Hiroyuki Ikeda was making his presentation. And so here's how I'm going to do this summary. I will give a general theme, something I've learned, some new idea at the top. Then I will give example, illustrating with each talk that someone here had given. And so I have just taken the stream of consciousness notes that I was typing during your talk, and I put it there. And so you might say, but that's not what my talk was. You wrote it down wrong. Well, this is what I heard your talk was, and this is what went into my mind, and then I will try to highlight with an underlining one key point, the takeaway message that I see is important from your presentation, even though I realize there were 15 or 20 minutes and many points were made, but I boil it down to one very simple thing, and then I'll move on. Okay, so this is a little bit crazy, but the only way that I can do a fair job to summarize everything that's going on here. All right, so my first point here is something that we need to remember, which is that this entire NEP collaboration, all of the scientific projects that we are doing, is completely dependent on extremely hard and not always very glamorous or fun work reducing the data, getting the data and reducing the data. And so I'm going to illustrate here that the people who are doing this, we are all depending on them completely for everything. It's like a pyramid that these people are carrying. There are real superheroes for us, and so because there are many ways to be a superhero, it's not just a Hollywood movie. Sometimes it's really hard work. And so I was really impressed by the work, for example, Ikeda-san told us about. In particular, what I was amazed to learn from his talk is that even such a sophisticated effort of science and engineering and technology, such as HyperSupremeCam, with a very sophisticated data pipeline, even by the time they got up to version 4.0, in my opinion, honestly, does not work adequately for the purposes that are needed. It does not subtract the sky properly, it doesn't detect sources correctly, and so we are very, very grateful that by the time version 6.5 has come along, I think this is really apparently the first time that these problems have really been solved. So we are direct beneficiary of all of these really painful, hard work. And so one point that I would make here is that even if we have a lot of problems with deciding on the photometry in different bands, we really want to be confident that the color information, the flux ratio in all different bands is the correct one that we can use. In many cases, it's okay if we are off by 5 or 10% in some absolute level about the brightness of the galaxy, but I really want to have all of the relative photometry to be as accurate as possible. And I think that the software is working pretty well to try to do that. All right, so there are more data reduction heroes. This is just the first one. And the nice thing is they're working together, which is really important. So Shangbin Kim presented really, really difficult work on finding the sources and band merging, which is absolutely critical. It's not just good enough to find the sources. And so this HyperSupremeCam data is a great improvement over anything that we had before, over the entire field. This Clean 7 catalog is really wonderful. One point that I thought that Songjin made, which is really important, is the final data products that the superheroes are producing for us are going to probably have everything in them, including problems with warnings and flags. And so you, the user, must consider what do you need for your project. For example, do you want a very high purity because you cannot afford to have any fake or wrong sources in? for certain work that's important. So you must be very careful to clean the data then. Or maybe you are looking for statistically a very new object that you have other information about, and so it's okay if 1 out of 5 or 1 out of 10 of the sources is wrong. You can still do your science with that. So it really, you have to think very carefully about what you want. But the master catalog should allow all of these different type of approaches to be made. So of course I want to mention definitely that Nagisa Ahoy has done really, really important work on this, working together with these other superheroes. And so I'm very interested, for example, when she looked at the number counts that she gets from Hyper Supreme Cam, and she's very good at spotting issues with the data reduction. I think there may still be an issue about these relatively bright sources, not too many of them, but rather interesting sources, whether C model, whether they're being measured correctly or not. But anyway, it's really good to have all of these superheroes working on the team. So I just want to point out, these are the real superheroes of NEP, not really Hollywood superhero, but that's Nagisa there, running back to the computer. Yeah, I mean, it's a superhero if you can just wear that and actually run. That's pretty good. Anyway, okay, but then we have another set of people that this collaboration completely depends on, and these are the people after the data has been reduced, who then have to go in and take the first attack on the data. And they have to be fearless. So these are the shock troops of NEP collaboration. They are not scared to go in and analyze the data. They're just going over the trenches. There you see these people charging into, well, into no man's land. That's what they're charging into. So I give you a few examples of the shock troops who are working on this collaboration. So Toshiki Toba's talk I found extremely fascinating because he's looking and finding, this surprised me, that he's finding real Akari sources in the infrared which have no HSC counterpart even in our very, very deep data. So that's already a big mystery, it's a big discovery. And then he has followed up this discovery very far by making a pretty strong suggestion that he may have a fairly large, it's not a lot of numbers. You have to be very careful to clean all the data. But in the end, you have a workable sample of objects which might possibly be quite high redshift obscured AGN, which were not known, by any kind of optical-based study at all. So I'll say more about AGN in the future. So that's a fearless attack on the data. It's a good example, but I have more examples of that. All right. Wada-san has used the SPIRE data, which is another from, also PAX data from Herschel, which is another wonderful piece of the NEP treasury of data, and compared to in the spicy galaxies, which I still believe is a not fully exploited resource that is unique, again, to Akari NEP. Where he has direct spectroscopic measurement of PAH, and he can look at the fairly good, excellent correlation between the small grain PAH emission that he measures and then the luminosity of the far infrared, the cool dust grains at 160. That is a fascinating frontier there. I find that a very promising work. Now, of course, one of this officers, that's you, Dennis, there, in the fight, he's in the trenches, but he's also leading the men and the women to charge out into no man's land. We're depending enormously on Dennis for all of his work with Segale. I mean, I don't know how this collaboration could really succeed without it. And he also, like these other people I'm showing, has been very productive in getting things done and publishing the results. So this is a good model for us. And so he has a really nice catalog trying to combine all of the wavelengths of data in it. The presentation that you made I found absolutely fascinating because of the idea that we may be able to use limited submillimeter data to basically make a prediction about the infrared continuum and the dust contents of galaxies even at high redshifts. And it's very intriguing to me. Anyway, assuming that this approach is reasonable, then one of the things that I took home from this is it really shows that the simple ideas that people have had, including us, have had, that all you really need to know if you want to predict the infrared that's supposed to be ultraviolet. If you want to know the infrared to ultraviolet ratio, which basically is a measure of how much extinction there is, it's just a function of only the stellar mass. Now, I think your work is already indicating there's more. It might be a function of redshift, perhaps because of the metallicity of high redshift galaxies being lower. So I find that very interesting for a future. It's very important that we add X-rays, of course. We have good data already, and E Rosita is coming in. So these are crucial steps that we're going to exploit as we march into no man's land. All right, other examples of this. Yoon-Bin Kim is doing really nice work. This is really hard work in doing quantitative morphological classification of these images. As you know, it's difficult, but we have pretty good image quality for a ground-based telescope anyway. And so there are many goals here, but the thing that I found most interesting about what she's gotten so far is a really intriguing result. She has made, I think, reasonable separations of galaxies, let's say, which have sort of normal star formation rate for their given mass, or some galaxies which have very enhanced star formation for their given stellar mass, or shut down, reduced star formation for their stellar mass, so more old, red, and dead galaxies, and these are starbursts. And there really was no correlation that I could see with the morphological parameters that she measured that might indicate, for example, interaction or merger, except at the highest redshift, where it looked to me like her result, the numbers weren't huge, but it looked like it was statistically significant that the higher the specific star formation rate is, the more likely you are by a substantial amount to find evidence of quantitative evidence of merging and interaction of the galaxies. That's a really interesting lead. I hope, one thing I will say generally, I hope we could get some higher resolution data maybe in future from space on some of the NEP field. Now, this technically is not directly about the data, but I think it's so extremely important to have a good physical model of what could be producing the dust in these dusty galaxies, which we typically are studying here. So I think it's extremely important for us to understand Takagi's work with SCIRT. It looks like a real step forward, particularly because it might be easier to use. And so there were many interesting things that he presented by using some SCIRT models, which I not specifically for individual galaxies in our sample, but generally probably applies to many of the galaxies in a Akari NEP field. And he's very modest, so he probably was irritated when they said that. But I really was very excited by the images that he showed of 850 micron emission, where you clearly see these dust halos, maybe scattering in cold dust, which surrounds very dusty galaxies. Depends somewhat on the geometry of the galaxies, but I could predict that some point day with an interferometer that will be measured, and everybody will be really surprised, except the people in this room, because we heard it first when we were here in Taiwan. We learned about the Takagi effect, and so we knew it was going to happen. So, so I think that was one of my favorite parts. All right, so what is another science topic besides just attacking the data? So we have, in this collaboration, we really like friends of friends. It's a very friendly collaboration. And so that is a very nice way, as we've seen, to pick out either large-scale structures or maybe physically bound clusters. We have to worry about whether they're actually virialized by gravity or just in the process of assembling. That is something to think about. And so I was very impressed by both Tetsuya's and Kevin's work, let's see, to find candidates for clusters in NEPY. Tetsuya was doing related work with Data Release 7 of Sloan Digital Sky Survey. So we had a number of talks here, although they're not specifically about NEP. I consider them to be related science, where it might give us some suggestions, some idea what we might want to try to do in NEP observations. So my favorite thing about Kevin, and so Tetsuya, of course, by able to cover a very large region of sky, even larger than NEP can cover, found this amazing 8 sigma over density, which is a fascinating cluster. And when we figure out exactly when he figures out exactly what's going on there, it may be a really serious challenge to sort of standard cold dark matter predictions about why galaxy clusters should form or not form with so many blue galaxies inside them. Now, Kevin's work, the thing that excited me about that was that he independently seems to have found, I would say, clusters or candidate for clusters of galaxies by his method, which then he didn't know it was going to turn out the way, also turned out to correspond in many cases to spikes that we see in the redshift distributions. He wasn't using spectroscopic redshift, so that was very, very encouraging that a completely independent approach is able to find dynamically related systems. So I like the friends. All right, what's another big theme scientifically that the troops in NEP collaboration are doing? Well, this is related to a Hollywood blockbuster movie which was based on the best-selling novel by Tom Clancy. You know what I'm talking about. The Hunt for Red AGN. Everybody familiar with that? It's great movie, great book, and so on. The hunt is on for Red AGN, clearly. We have several leaders of this hunt who are doing really successful work, probably more successful than Sean Connery was in that movie. They sunk it. All right, well, he escaped. All right, so Wongse has used these new KMT observations, which I think are a very exciting addition to find new dogs. Okay, so these are selected at 24 microns, and then they're very red in the optical, so they are extremely high luminosity, probably at rather high redshifts there, of around 2. And what he proposed, he gave evidence for you, is these are AGN dominated. These dogs, that's very important, but this is much better. He has actual proof that they are AGN dominated. In fact, they are Seaford-1 dominated, not really Seaford-2, but you have to look at H-alpha. H-beta will not do this for you. So you have to go pretty far in the infrared to prove that there really are broad wings to the H-alpha in these objects. H-beta won't do it. So this is an important step forward. I really like that. I would like to see more of that. Meanwhile, Tina Wang has been using multi-band SED fitting, and we can see that this is very powerful now with Sigali. It's been improved to handle this, and it really helps to have the Spire data included. Of course, it would also help, it seems to me, to have more spectroscopic redshifts as well. But anyway, I was pretty encouraged that when the AGN fraction that Sigali tells you is reasonably high, above a half. This agrees essentially perfectly with what we've learned from the spectroscopy when that's available. However, there is certainly an interesting gray area. When you get below an AGN fraction of 30%, maybe 10 or 20%, I think some of these galaxies might be classified spectroscopically as just star-forming galaxies. That might be because the AGN is in there but too obscured, and so we should be aware of that. I suspect that many of those objects are really composite galaxies where the question really is how much is being produced by AGN, how much is being produced by star formation. If this is right, if this holds up, I mean, don't you have an average fraction of AGN light, of luminosity of something like 10%? That's a pretty high number if that holds up. So it's an interesting question to see what we can learn statistically from these small percentages. I mean, are they real or not? If they are, that's very important to know about. All right, so on the hunt for AGN, we're studying SEDs that we get. These are uniquely produced by Akari plus the multi-wavelength data, and so it's a very exciting hunt. And then I felt so embarrassed because I'm just like, this was the first time I really felt getting maybe a little bit old at this meeting. I was just playing dominoes to look for this, and here's my AGN cat card, and there's my composite AGN card, and I realized this is so 20th century. Look what I'm doing here. Nobody plays dominoes anymore like that. This is too primitive. It's all been replaced by computer games. You don't even want to have humans involved in this. The future is with computers, and I'm beginning to take this seriously, actually. one of the first things I learned really clearly here is we are now looking directly at, in this collaboration, something that's sweeping the world here. I call this the rise of the machines. Yes, the machines are rising here, clearly. I mean, again, another Hollywood blockbuster. Everybody in the culture outside of me knows about this, and so machine learning is really going to change astronomy as with everything else. So we had a number of talks which began to persuade me about this. I was too old-fashioned, but I think I'm getting excited about it. So Simon Ho had many discussions about how to get good SEDs with multi-band photometry at all these wavelengths. It's a lot of work to do it. You don't want to give a machine bad stuff put in because it will give you bad stuff put out. But if you put good stuff into the machine, then it can work well. This was not even the point of Simon's talk, but he said, you know, I tried many different ways to get photometric redshifts. It's really difficult. I think fundamentally, after we had many other hypotheses that Simon tried and shot them down for us, I think that the fundamental limitations at the moment why our photometric Z's are about as good as they are, especially at higher redshifts, is just the filters that we have available in our data set for NEP. So that's difficult to improve, really, but this was not his point at all. But I admire Simon for trying machine learning, and he said, hey, it works just about as well as any other method that you used, I think. Well, that was interesting, wasn't it? Not even designed for it particularly. But I think one of the beautiful areas where machine learning is really strong is for classifying all of these SEDs to pick out interesting new objects, in particular AGN. It seems like this was made to do such a scientific problem, and even though I must admit that I was amazed how little I understood about what the machine is actually doing. And I need to learn more about it myself. But I did get some conclusion about it, which is, for example, from Artem's talk, that you, of course, want more wavelength bands. The more, the better. But even if you just have 6 bands, these are the Akari bands here, just 2, 3, 4, 7, 11, 15, and 18, which we have for a lot of objects. That works fairly well, and then you must have, in particular, the near-infrared colors. Okay, that made me very happy, because I've always thought that the hot dust is the very distinctive signature that is going to really find us many AGN, regardless of whether they are obscured or unobscured objects. It doesn't matter how dusty they are. We will find them. The machines will find them. We'll take them, right? They can't escape, is what my point is. The machines will find them. So Oliver, I thought, gave a very encouraging talk about this too, particularly because it's, as I understand, using really different methodology. It's deep learning. I heard about that, and it had many layers. You said it's like the human brain works, which, okay, probably better than how my brain works, but the result I liked very much, that we can have really fairly good recovery of AGN when they're known with fairly small errors, and this looks like much better than traditional methods. So I know there is more work to do here, but I started probably being skeptical before I came to the meeting. Now I'm getting kind of excited about it. I think it's probably the future way to go. All right, so that covers many of the work that the NEP troops are doing in charging and attacking data. Sorry, it's going on a little bit too much, but I have more to talk about. We also heard some really interesting talks about what I would call NEP-related science. So we didn't shut the door and keep the people out just because it doesn't have NEP data in it. I'm glad that they were allowed to come in, because they might have given us some new ideas about analysis that they have done on other really nice data sets. We should consider, do we want to try that for working on NEP data? Is there some way that we could apply what they've learned to learn something about NEP? I think it depends. I'm not terribly enthusiastic about simply trying to catch up to repeat some other work that somebody else has done better in some really big, very deep, large field where they really have tremendous data. We need, however, to try analysis and to try methods where the Akari deep field has some unique advantage. And we all know what the unique advantages of Akari deep field are. They're particularly from the infrared camera, the 9-filter infrared survey. So, and in fact, by the way, you don't have to have all detections by Akari. If in some cases Akari has very good upper limits in these infrared bands, that could be used also to do some of the science. So, if you have, for example, very good K-band imaging, Jung Jae Kim showed some very nice work, and this is known. You can use BZK method, or you can use a very red R-K to find interesting objects at redshifts of around 1.5. So that is, I think that's an interesting area, because we do have a sensitivity in Akari NEP to get there, although we're sort of running out at the moment. I think it's the frontier of NEP. So I like to see if it's possible to do some of that work for NEP objects. And okay, so we have some of these data sets. In fact, we have superior data sets in some cases. Young-Soo Cho showed that you can pre-select galaxies at these interesting intermediate redshifts with, for example, IRAC 2-band selection. And in this case, this turned out to be maybe an interesting way to find candidate clusters of galaxies. And of course, I'm also interested in any synergy we can have with Akari Deep Field South. There are some overlapping science there. And as we'll see later, having this KMT network of 1.6 meter imaging telescopes with large imagers can really be useful. And so they are finding ULERGs and following them up with the IFU and Gemini. I think that's going to be really nice work, and it might give us some ideas what we could do in NEP North. Oh no, this one's going to sign in again. I hope I'm all right, more NEP. Stop doing that. More NEP related science. Okay, I'm always interested in what Yuriichi Oyama talks about, and this is a local galaxy not connected directly to NEP at all. But NGC 4418, if you don't remember it yet, maybe it's not the license plate of your car, but it could be. This is a wonderful galaxy because it is extremely compact, has enormous infrared luminosity in a very, very small volume, and we don't really know why or how it does that. And one of the fascinating clues I didn't really realize that makes this galaxy so unusual is the radio emission. We have an idea about what the radio emission should be produced by star formation, should be producing a certain number of supernova remnants per year. The supernova remnants are supposed to produce synchrotron emission with a steep radio spectrum. This galaxy breaks all those rules. It doesn't have the radio emission. The radio emission it has there is really largely free, even not the synchrotron emission. And the fascinating idea is that this galaxy, and maybe a few others, maybe 1% of the ULERGs, which we're already interested in because of their very deep silicate absorption, maybe these galaxies, as revealed by the weak radio synchrotron emission, might be just caught by luck, especially in a very early phase of their starburst. I don't know, but that's a fascinating lead to pursue if we can find such galaxies in NEP. All right, now can I get this thing to go? Yes, all right. So other examples, all right, so this is an amazing survey that Anna presented us with, the VUDS Galaxies Spectroscopy Survey at high redshifts. All right, we're not going to compete with that, honestly, at this point, but if you can get data of that quality, it is fascinating how much you can learn, perhaps about their dark matter halos, by basically looking at clustering, starting with the 2-point correlation function, and maybe some more information as well. You look at it as a function of stellar mass and luminosity, and it's getting to be pretty sophisticated models where we have a minimum halo mass required to have any galaxy at all, and then we have a larger halo mass where a satellite galaxy can come in. There were a lot of data presented, a lot of analysis presented there. The one take-home that I got from Anna's talk is, well, there's some kind of problem with the low-mass galaxies, I think is what she said. And it's not clear. Either these galaxies have formed too many stars. We're talking about a factor of 10. That's a kind of a problem, you know, even me as an astronomer. I don't worry about a factor of 1.5, but 10, I think it gets my attention. Or perhaps it's the other way around. The halo masses are too small for what we've inferred. Okay, so that I found interesting, although not immediate. I don't know how we would immediately connect that to NED science, but we should be aware of it. Maybe we'll find something interesting to be inspired from Jimmy Ling's talk about the central surface density of compact galaxies. That is an interesting problem, which is not really entirely understood how they can get to be that high. I'm particularly intrigued by the possibility that our galaxies might have nuclear star clusters in some of them, which maybe were sites of extreme star formation in the past. I'm not sure how much we can do really on this without very high resolution imaging. So I don't know, but I know it's an interesting area that we should be aware of. All right, now really going further astray. So these are some other interesting science that we heard about. Just to remind you, I found it very interesting. I'm not sure if it's going to be connected to what we're doing at NEP, but I'm glad to know about it. Mostly I especially was impressed about her discovery of a new, very luminous Lyman alpha halo with that very expensive custom-made filter that they got for Subaru around a redshift 6.42 quasar. Now, she had some very intriguing suggestion that she may be seeing systematics, that these Lyman alpha halos may systematically correlate with the objects that they're around. For example, even the mass or the luminosity of the quasar. That's not a crazy idea. And so it's a very exciting lead. We'll know more, I think, when we have more than 4 objects to look at. At the moment, I'm not sure of it yet. But I know it's very interesting to find out, because this is one of the only ways that we can study whatever the gas is around a galaxy. We can call it the circumgalactic medium. I don't really know exactly what it is or what it's doing, but it's usually invisible, unless we are lucky enough to have a quasar light it up for us and study Lyman alpha. And then, of course, another thing which is interesting about the effect that a quasar has on its surroundings was presented in very nice work by Nicole Liu. I think the most interesting point of this was her measurement, and it's a very careful measurement of how far the near region, this is an ionized bubble that a quasar makes around it of ionization, how far out from the quasar does that extend? And so you got a good feel for how this can be observed now. You need high redshift objects, and so this ShellQ project is really wonderful because it's giving us a lot more kind of typical, not the ultra-luminous, most luminous quasars in the universe, but sort of average quasars at a redshift of 6. I didn't even realize there were 64 of them. I mean, that's wonderful. So I enjoyed that. All right, so you've seen a lot of good science here. It's always nice, though, I think, to take a chance. Do some people like to gamble occasionally? Every once in a while, it's fun. Maybe you should take a long shot on something. So here's an example of that. Okay, this is an actual picture of this guy in Brazil. He had put essentially all of his money on number 32 on the roulette wheel. And you see the result. It came up, number 32. And so if you don't try, you won't win here. So I thought that's my attitude about taking some long shots. So Ihan Wu's proposal to use the CO line to basically measure the dynamical mass of galaxies, even if they're infrared galaxies at high redshift, and then correlate that with some luminosity of the galaxy. It's basically a kind of a pseudo-Tully-Fisher relation. Well, as I said, if this can possibly work out at all and can be tightened to reduce the scatter, then he's going to feel exactly the same as this guy in the picture there. It'll be very important. I felt that way somewhat also about finding redshift 9 galaxies with Scuba 2. It is, I don't know, it's possible. I mean, we don't need to worry about theories. As an empirical matter, we should go check the data. And if we have enough sensitivity at 450 and so on, then maybe these 31 objects, maybe some of them really are among the highest redshift galaxies. It's very important to find out. Even a few of those would be a big deal, a very big discovery. Anyway, so I just remind everybody pursuing this, I guess I would tell the guy in the casino also, it's what Carl Sagan said. And if you're going to make an extraordinary claim, you require extraordinary evidence to back up that claim. So we also even had a theorist's corner. There's a theorist's corner over there. By the way, I like this picture because it's the relation. This is George Ellery Hale at Pasadena. I've been at that blackboard many times here. He's looking down at the theorist there and the theorist is looking up at the astronomers in the room there. That's the library where we give our talks. And so I was fascinated, for example, to learn from Albina that the SKA is essentially going to make magnetic field measurements using rotation measure of so many galaxies all over the sky that they will have a grid of the entire sky. And that just was mind-blowing. And so now she's thinking about what you could learn about the evolution of cosmic magnetic fields. That would be, as you know, the amount of ignorance in astronomy is always directly proportional to the strength of the magnetic field. All right. That's a joke, guys, but it's true. All right, and maybe slightly more related to what we are studying about dust-driven winds, Hiroyuki Hirashita's calculations. Convinced me that actually these galaxies probably are blasting some amount of dust into the intergalactic or circumgalactic medium around galaxies. They probably do have these dust grains, especially he showed us if they're rather small grains, about not too small, not too big, then they can be driven out by radiation pressure. So I guess my message to the theorist's corner is please keep thinking about these ideas, keep looking at the observations, and come up with some observational signal that we could have a chance to measure. And if you give us a clear prediction of something that we can measure, we will go out and try really hard to try to test your theory. That's what we want to do. All right, so that's the theorist's corner. Now, what about the future? This is really the main purpose here. All right, so the future of this field and this collaboration and NEP is really wonderful, and that really means, well, particularly for younger astronomers. So you could pick many other areas, but I think this is a really good one, which can carry you, through some stages of your career with having many new findings. So, for example, the wide North Ecliptic Pole region is, this is not in any particular order, but if we could have a really beautiful spectrum, including infrared coverage, right, of every object in the entire NEP field, maybe also in Akari Deep Field South, down to 20-second magnitude, think of what a game changer that would be for everything we are doing. It boggles my mind. I think this project is so brilliant that it has to be done. And it's a project that could go on a faster time scale than some of the other bigger flagship projects that we'll be looking at here. Let's see. All right. So now what can be done right away? All right, very soon. So Ho-Seong mentioned and I completely agree with this, the serious need that we have for more spectroscopy, more redshifts, and also more emission line diagnostics for NEP galaxies. We've worked on it hard, but the possibility of their using heptospec, using Korean time, to maybe get 10,000 of the relatively brighter NEP galaxies, it really is possible to do that. That really will be getting a jump, a head start on anything that PFS will do later. Of course, we should think about PFS also, but we'll already be doing a lot of their science. I also like the idea, Jingle's interesting idea, I love the idea of a large project with JCMT for CO spectroscopy. That's an area we have not exploited much yet. So those were kind of new, exciting ideas to me. All right, then we have a talk here from virtual Matsuhara-san. He presented the talk and his ideas. So I hope everybody knows that eRosita is supposed to be launched on July 12th, and it's going to change everything. At least certainly for any kind of objects that emits X-rays. That's not just AGN or obscured AGN maybe. In some cases a starburst could give you X-rays. Certainly galaxy clusters can be detected by eRosita. It goes out to hard X-ray energies, 12 kilovolts, which is wonderful. So that is a game changer, and we, of course, we got to put all these collaborations in place now, particularly with the Russians, particularly with Sunyaev, because they own the North Ecliptic Pole. Remember when Portugal and Spain were exploring the New World, they divided the New World in the Treaty of Tordesillas, and Portugal got the nearby part. They thought that was the best deal, so they got Brazil, Spain got everything else. So we want to make sure that we talk to, I think, to the Spanish in this case, or no, the Russians, I think. They have pretty much most of the New World in their part of the treaty. So I'm not sure what X-RISM may do for the brightest X-ray sources in NEP, so I put that in there. But I'm certain, and this one we really have to be preparing for, I brought my Spica t-shirt with me here, and this is going to be an absolute game changer when this goes. And even though the launch won't be for a long time, the planning for the instruments, the capabilities, and the surveys, what are going to be the key projects they will do, that's happening now. So you can have it. What are the fields that they're going to do? What do you want? Well, Wada-san gave a really interesting proposal, for example. How about a blind spectroscopic survey of 10 square degrees? This takes 500 hours. You could detect 50,000 galaxies from their PAH emission, a significant minority PAH. And think about how that would change the scientific landscape. It's just stunning. Anyway, so this is particularly where you might be the right age, that you can be prepared for that in 2030, when I hope it will happen. All right, let's see. I think I have one more, a few more things here. Sorry, it just keeps on coming. Closer to home again, I'm excited about the sub-millimeter data that we're getting from JCMT now, because, as you said, it has great advantages over the Herschel data we have. For example, even just already looking at the sources, Hyunjin showed us 330 detections. We have to be careful about what signal to noise we're willing to go down to, for what purpose we want to do. But the future of sub-millimeter astronomy and millimeter astronomy is really exciting for us. We should be all over this, because we really do have unique contribution to make to study of millimeter galaxies. So, and we have a millimeter telescope in the northern hemisphere that's ready, getting ready to do this. So apparently, since it's in Baja California in Mexico, the large millimeter telescope, and you know it is very large there, it's really designed to do this kind of thing, is going to have a super array, I guess it's like a super scuba 3 kind of array, where it simultaneously can get 1.1, 1.4, and 2.1 millimeter bands. These are wonderful for high redshifts, as you saw, because of the very favorable inverse K corrections, right? The galaxies don't get fainter at redshifts of 2, 3, 4. They're the same. Maybe they're even brighter as we measure their infrared dust peak. And LMT gets down, it's supposed to get down to 0.3 millijansons. This is just mind-boggling. Now apparently, since it's in Mexico, every single new exciting instrument and project has to be named after some Aztec thing. Or whatever, Toltecs came before the Aztecs anyway. So that's okay with me. We can, whatever. I hope, though, we're not doing everything, you know, of the way the Aztecs did, you know, because basically some sacrifices might have to be made there. Anyway, but basically that's Aztec. Oh, sure. No. Anyway, well, let's see if I can get this thing to start again. Oh, God. All right, let's see if I'll get it to go. So, that was almost the last slide, actually, but there's one more slide, you gotta see it, so never mind. All right, let's see. How do I get back to that? I want to see most recent things done. What do I do? Yeah, start PowerPoint up again. All right, so we go to recent files. Open recent. Okay, there it is. All right. Okay. All right. Okay, there we are. Just 2 more slides here. All right. Don't crash now. All right. So yes, of course, we're welcome. We should always. My point about what Toft said is we should always strongly welcome collaborators. These are the greatest collaborators. You know, it's like they came down from heaven. You know, it's like the guys coming off the ships. So we should do everything we can to link up with them, because this Cosmic Dawn survey is an incredible opportunity for both of us. They need us to some extent, and we really can benefit from working with them. So, in particular, it's all about Euclid. We have to really be prepared. They realize this is the time right now to start getting ready for the Euclid deep field at 10 square degrees, so even larger than NEP wide, centered on that region. And it's going to be fantastic, particularly when you consider the amount of preparation data they already have in hand. The 6,000 hours of Spitzer data is just, think about that, it's mind-boggling. The beautiful near-infrared photometry that they have from UCURT. And the beauty, think about the complementarity of this. I mean, he just told us right out. He said, he is really the only person on that team that is particularly interested in the galaxies of redshifts of less than 2. If you look at the team, which is where we really own it with the Akari, if you look at that team, they're all going to do fantastic science above a redshift of 2, 3, 4, 5, 6, 9, or whatever. That's how the entire proposals, I've read some of these proposals, are set up. But as a byproduct, serendipitously, they will produce an incredible gold mine of data for us. All right, so that's a must. Now my final thing, and I have to have the slide for this, my final summary, I cannot fail to make one very important point here. I found this. I can simply not imagine where we would be without Tomo. I mean, Mansa Harasan really, of course, might be sort of the godfather of this whole thing, and you were there, and it's fantastic to have him included, but he's also brought in other people as well, particularly ground-based observers, and this has been a fantastic thing. It's just hard for me to imagine this collaboration without Tomo being involved. You know, this is a guy who leads the way and runs here. If you went into his office, like I couldn't really sit down with all of those trophies that are in there. Apparently these trophies are from running a marathon, which I knew that you did, but I mean, I don't know that he has any time to do anything else with these marathons, and there are so darn many trophies there, apparently. So I thought, well, okay, I guess it's so hard to run a marathon that if you can finish the marathon, you get a trophy. But apparently you actually have to finish faster than other people. I think that's what he's doing here at the red tape. And you know, it's not just that there are 5 or 6 guys running 26 miles. Look, this is number 1461. Right. I mean, I don't know, unless they started the numbering at the, 1400. That's really, that impressed me very much. And so I realized, the NEP project is very much like that. We're in here for the long term. This is not just a 100-meter sprint. This really is a marathon that we're doing. It's been going for years, and we still have a lot of tapes to cross and a lot of prizes to win. But in the marathon, the one thing that you would like to, okay, this is not true of his marathon there, but somebody has to be running in the front there. So we have a leader with a real experience of winning. And so one thing I know about Tomo is that if he starts going in a particular direction, now with a marathon it's easy because it's marked which direction pretty much you're supposed to go. We're going in some directions that we know and some directions we don't know. But once he starts in this direction, you know he's going to get there. Okay, and maybe before other people do, and if we follow that lead, then all of us will get there also. All right, so thank you, Tomo.
Where did you find this picture?
It's all over the internet. In fact, it just takes a second, guys. All right, let me see if I can just find this one thing, because I guess not everybody knows.
Oh my God!
All right, so let's get this one. Well, there's tons of these too. Okay, so watch. There's one important point about this. All right, so I guess the tape means he's the first one.
Oh my God!
Look at that. Okay, most people would say, "Thank goodness I got to the end of the race. We finally published this paper here." But Tomo, you don't have to jump over that thing. It's making it more difficult. What is the, I can jump over it. I've been running 26 miles. I feel like jumping. It's not a high jumping race. Anyway, so I love that. That tells you a lot there. Okay. Anyway, then it goes on. I wasn't really able to follow some of the other stuff here. I don't know what he's saying, but you know, that's why there's like, there are no journals and anything. He's got all these medals there in the back. Yeah, even the medal with a horse on it. It's actually a marathon medal because you can almost festival. All right, so that, I just wanted to show you that. Okay. So I hope maybe this gives some ideas of some of the strengths that the collaboration has, some of the things we need to really try to do, some dangers that we have to worry about, and then what the future is for new analysis and new observations. That's one of the real value to me of having this kind of meeting. So I'm sorry I wasn't here last year. I really enjoyed this. All right. So do you want to go in now to discussion for the future?
Yes, we should. I forgot what to say after.
What can you say? I didn't think you'd be able to say very much, but that's okay.
So maybe we should say comments and
Well,
questions.
I have one comment with the dominoes. Now you know you can play dominoes on computer.
Oh no.
Something you can do, and they even wrote a mechanical domino-based computer with 10,000 dominoes. You can play
Jeez. And so does the computer always beat the human opponent?
Yeah, I mean, if you play like this all these rounds on the computer, you can do it easily.
Yeah.
You can mix your approach with computers.
Yeah. The only way I could win, of course, is if they programmed the computer to make mistakes. Otherwise, which we're not going to do, not deliberately. Although that HSE pipeline 4 sounds a little bit like that. But, yeah. It's good to know. But you want to take a break before we have a discussion?
Yeah, I think.
Yeah, is there a coffee break? We can do
Yes,
it.
I think Snap is waiting. So any other questions or comments? Okay, so maybe we can come up